So we're going to do a couple of more examples of these limits at infinity. And so let's look at the limit as x goes to infinity of x minus x times the square root of x over 2x to the 3 halves plus 3x plus 5. And because we've got this mixture of these fractional powers and radicals, we're going to rewrite the whole thing in terms of these fractional powers. It's going to be a little bit more convenient. And now we want the limit as x goes to infinity of x minus x. Well, let's see. This x is really x to the first. We know the square root of x is really x to the 1/2. What do we do when we multiply something with an exponent by something else with an exponent? We add those exponents to get x to the 3 halves, all divided by 2x to the 3 halves plus 3x plus 5. And from last time, we know that we are going to divide everything by that highest power of x in the denominator. And so the highest power here is that x to the 3 halves. So we get the limit at infinity of x minus x to the 3 halves over 2x to the 3 halves plus 3x plus 5, and everything is going to be divided by x to the 3 halves. And then we'll simplify that. So limit as x goes to infinity of, well, x to the first divided by x to the 3 halves is going to leave us with x to the 1/2 in the denominator. X to the 3 halves divided by x to the 3 halves is going to leave us 1. And all that's going to be divided by, cancel those guys, leaves us a 2. X to the first over x to the 3 halves, 3 over x to the 1/2, and 5 over x to the 3 halves power. And if you remember our little fact from last time, the limit as x goes to infinity of 1 over x to the n is 0 as long as n is positive. So any x in the denominator, and really we want some sort of constant in the numerator. So it can be 3 over x to a power, 5 over x to the power, or it could be 1 over x to some power. As long as this is just x to the n in the denominator, we're going to use this little fact, and that's going to make 1, 2, 3 of the terms in our expression go to 0. And we are left with this -1 and the 2. So our limit is -1/2. This value, or the horizontal line, y equals -1/2, is called an asymptote. Of the graph, y equals x minus x squared of x over all that stuff. So we're going to graph this here in just a second. But an asymptote, in this case a horizontal asymptote, is a line that our graph will get closer and closer to as x goes to either infinity or -infinity. We can have two different horizontal asymptotes. And in fact, that was exactly the case for our example last time that involved an arctangent. And we had another example where we had different limits as x went to positive or negative infinity. I say the graph is going to get closer and closer as we go off to the right or off to the left. I did not say that it can't cross an asymptote. The graph can cross or intersect a horizontal asymptote. And I'll give an example here in just a minute where that is exactly the case. But the point is that it's going to get closer and closer and really stay close to that horizontal asymptote. And in fact, the graph for this guy, if we graph, you can do this on your calculator. I'll have to write a little bit of extra for you to use when you graph it. If you graph y equals x minus x square root of x over 2x to the 3 halves plus 3x plus 5, because we have the square root of x, because we have this x to the 3 halves power, this is only defined for x's that are bigger than or equal to 0. And the graph looks something like this. And that line, y equals negative a half, on our graph is going to be this line. So our graph is going to get closer and closer and closer to this line. In this case, it's not actually going to cross it, but it certainly can. Again, I'm going to give you an example where that happens. I will point out that if you are going to graph this on like your little TI calculators, or even on Desmos, because it's pretty smart, but it's not quite smart enough to give a good graph of this. You want your y min to be -1 and your y max maybe to be +1. The default on a TI are plus or minus 10. And that's not really going to give you enough detail where you can see this little wiggle here. This only gets up to, we have the tools that we need to find maximums and minimums, but this only really gets up to like, a half or so. So we need to make sure that we can see, and we sort of stretch this out vertically, be able to see all the detail. But the graph's going to look something like this. So our horizontal asymptote at y equals negative a half. Some more examples of graphs with these horizontal asymptotes from last time. We had the limit as x went to, in fact, we did plus or minus infinity, x squared minus 1 over x squared plus 1. The graph of this, and we found that we had horizontal asymptote at 1. Our limit was 1, and that was true whether we went to positive or negative infinity. And go back to the beginning of the previous lecture, and you'll see all of that. The graph for this guy, we have that line at y equals 1. Comes from our limit. And this looks something, I believe, actually it dips down here like that. It looks something like that. So forget about that part. The graph is going to get progressively closer and closer to that line as we move off to the right. It's going to get progressively closer and closer to that line as we move off to the left as well. And we call that, again, a horizontal asymptote. The function y equals 1 over x has a horizontal asymptote at y equals 0. Our little fact that we use tells us that that limit is 0, and those limits are what give us the numbers to form these horizontal asymptotes when we graph them. And we know what the graph of y equals 1 over x looks like. So horizontal asymptote right there at the x-axis, and the graph is going to get closer and closer to that, either from above or below, depending on which direction we go. In this case, we actually have a vertical asymptote where the denominator is 0, but maybe the numerator is not. It's maybe a little bit more complicated than that, but that's going to be a good rule of thumb for us, is a denominator of 0 where the numerator does not go to 0. While a graph can cross a horizontal asymptote, it cannot cross a vertical asymptote. That's simply an undefined value of the function. If we look at the graph of arctangent of x, and I have that around here somewhere from last time, the graph has a horizontal asymptote at y equals pi over 2, and another one at y equals minus pi over 2. So again, the graph's going to get closer and closer to that horizontal line as we move off to the left. It's going to get closer and closer as we move off to the left here and the right there. And we determine those horizontal asymptotes by finding these limits at infinity and negative infinity. One that actually crosses a horizontal asymptote y equals, say, the sine of x over x, is going to cross its horizontal asymptote an infinite number of times, in fact. If we find the limit as x goes to infinity of sine x over x, well, the numerator of our fraction is going to stay between negative 1 and 1, whereas the denominator of our fraction is going to get very, very, very large. And so we're going to see the overall value of this fraction get smaller and smaller. And the graph for something like this, at least away from the origin, it's going to get a little bit trickier as we get close to the origin, is going to look something like that, where the height of our little sine wave gets progressively shorter and shorter. And so the graph actually does cross this horizontal asymptote, but it does so an infinite number of times. So y equals 0, horizontal asymptote there. So let's try another one. Let's look at the limit as x goes to infinity of x to the 4th minus 3x squared plus 2 over x cubed plus 1. The highest power in the denominator is x to the 3rd, and so that's what we're going to divide by. I don't care what the highest power is in the numerator. I only need the highest power in the denominator. Our goal, the reason we divide by that, if you go back to all of the examples that we have worked so far, is to get us to the point where where we have some sort of constant left over in the denominator. So that's what that division is really doing for us, is getting rid of the fact that we've got this little infinity going on in the denominator and replace it with a little constant. So we're going to divide everything by x cubed. So we take the limit at infinity of x to the fourth minus 3x squared plus 2, all divided by x cubed plus 1 divided by x to the third. And start simplifying. So the limit at infinity, x to the fourth over x to the third leaves us x. That will reduce to negative 3 over x. It doesn't cancel, I screwed that up. And this is left with 2 over x to the third, all divided by, those guys really do cancel, 1 plus 1 over x to the third. And our little fact says that these little reciprocal functions are all going to go to 0, but that x is not going to 0. And in fact, that x is getting as big as we want it to. And we say that that limit is infinity. In fact, this function still blows up at infinity. And as you work through some of these problems, you may start to notice some patterns that show up with these types of limits. We will talk in the next semester in Calculus 2, if you're coming back this summer. We will be doing Calculus 2 in July. We'll talk about some of the techniques that we can use to find some of these limits, even without going through this division. That's going to be a very, very powerful technique that's going to give us some more tools to work with. So our limit at this time is positive infinity. So let's try another one that maybe looks a little bit strange and is not going to look like the ones that we've got here. Say the limit as x goes to infinity of the square root of 9x squared plus x minus 3x. This is not over anything. Now, on one hand, of course, as x gets really big, this term is going to get very, very big as well. We're subtracting it. And again, as x gets really, really big, 9x squared is going to get really big. If I add x to that again, it's going to be even bigger. And if I take the square root of that, maybe it's not quite so big, but still pretty big. And we're left with something that kind of looks like infinity minus infinity. But since infinity isn't a number, infinity minus infinity is indeterminate. We don't necessarily know what infinity minus infinity is. It might be 0. It might be negative infinity. And this is going to be kind of strange, but just kind of stretch your brains for a minute. If this infinity is bigger than that infinity, then the result might be negative infinity. If the first infinity is bigger than the second one, the result might be infinity. If they're about the same size, the result might be an actual number. So again, this idea of subtracting infinities is kind of a weird thing to do. Now, we definitely can add infinity. Infinity plus another infinity is just super infinity. Infinity plus infinity plus another infinity, definitely, super definitely infinity. But subtracting these, it's hard to say how that's going to turn out. And so this is one place where simply applying the limit to each term on its own and then adding or subtracting the results does not work. We have to have the fact that these limits exist first. That works here, because we can apply the limit to this, and that limit exists. We can apply a limit to this term, that limit exists. We can apply the limit to this term, that limit exists. And so we can add these guys up in the denominator, we can add these guys up in the numerator, and then we're just sort of left to deal with this x. So what can we do with an expression like that to maybe resolve this idea of infinity minus infinity? We're going to rationalize. And we've seen this trick before with evaluating limits earlier this semester. In fact, we found the derivative of square root of x by using a little trick like this. We're going to multiply by 1 but written in a little bit of a funny way. Here in pink, the square root of 9x squared plus x plus 3 more x divided by the square root of 9x squared plus x plus 3 more x. This part obviously is 1. It's not going to change the value of our limit, but it's going to significantly change what it looks like. And then we're going to FOIL. And in fact, we don't even need to FOIL. We really just need the first and the last, because if you work out the inner and outer terms, you're going to see pretty quickly that they are going to cancel. Again, this is not a new trick. We've done this kind of thing in several cases before. And so now we're left with the limit of, if we multiply square root of 9x squared plus x by itself, we get 9x squared plus x. Multiply 3x times 3x, one of them is negative. We're going to get minus 9x squared. And then we're going to divide that whole thing by our denominator here. Square root of 9x squared plus x minus 3x. Our 9x squareds cancel, and we're left with the limit, and it's not going to fit, the limit at infinity of x over the square root of 9x squared plus x minus 3x. Now, what is the highest power of x in the denominator? Well, I have an x to the first here. If we ignore this term, because we're just looking at exponents, we have this square root of 9x squared, which is also kind of like a first power. So our highest power of x is x just to the first. Now we go through the same kind of trick that we did here, dividing everything by x. The limit as x goes to infinity of x over the square root of 9x squared plus x minus 3x. And now we're going to divide everything by x. X divided by x is 1. 3x divided by x is going to be negative 3. We want to simplify this guy, and we're going to pull the same sort of trick that we've been doing. 9x squared plus x. Rewrite that as the square root of x squared. And now we can combine these radicals into 9x squared plus x over x squared, the square root of 9x squared over x squared plus x over x squared is the square root of 9 plus 1 over x. I know that's a lot. We had to go through a lot of work just to figure out how to put this into the right form. And then we still have to go through and deal with the fact that we are looking at a limit of a radical or rational function and do this divide by x trick. All right. So what do we have now? As x goes to infinity, of course, this 1 over x is going to go to 0. We're left with 1 in the numerator, and the square root of 9 is 3 minus 3 in the denominator, leaves us with 1 over 0. Our limit does not exist. What's really happening is, we have this square root of 9x squared plus x, we have 3x, and, each of these has a graph. The square root of 9x squared plus x, I'll graph that real quick. Let's see, look at the standard thing and graph it. Kind of looks like that. This looks a little bit like an absolute value. But down here at the bottom, this really is not quite a straight line. In fact, none of this is exactly a straight line, although it kind of vaguely resembles one. We have this thing that is growing like a straight line. We've got another one that's growing kind of like a straight line. And if this one's getting bigger faster than that one, then our limit might be infinity. If this one's getting bigger faster, then our limit might be negative infinity. And if they're getting bigger at about the same rate, then we may get something in between. Again, and I realize this is sort of very vague, hand-wavy, non-obvious stuff, and that's okay. As you work through the limits, as you maybe look at some of the graphs and how the graphs are interacting, you may start to see that that some of these limits maybe kind of start to make sense. Again, we will have some more techniques in the second semester that will let us work with these types of limits as well. And I do realize that going through a lot of work to end up with does not exist, maybe kind of feels like you've been cheated out of something. And I do apologize for that, but them's the breaks sometimes. Okay. So we've got a lot of different kinds of graphs that we've worked with, a lot of different kinds of limits that we've worked with, and we've added to kind of our little bag of tricks for how we can work with limits. The idea of this horizontal asymptote is a line that our graph is going to progressively get closer and closer to as x either goes out towards infinity or negative infinity. And then the idea of a vertical asymptote is one in which the denominator maybe is going to 0, and the graph simply is undefined. We can have other types of asymptotes. We can have curved asymptotes. We can have what's called slant asymptotes. In particular, for functions like this, where the degree of the numerator is higher than the degree of the denominator, then we'll end up with some sort of slant asymptote. And in this case, if we ignore the other terms and just look at x to the fourth and x to the third, those would divide out and leave us with an x. And in fact, that's exactly what our slant asymptote is going to be. The graph of this is going to get close to the graph of y equals x as we look out towards the very far right of the graph and the very far left of the graph. At any rate, not all of that stuff is going to be useful or interesting to you, but there's a lot of information that we can get out of these limits at infinity and asymptotic behavior. And in fact, asymptotic behavior is one of the key tools that we have for analyzing lots and lots of different kinds of systems. It's something that we're going to see more in next semester when we get into determining areas under curves. It's something that we're going to look at most definitely when we get into the third semester in the fall and start talking about sequences and series. And it's going to be something that we work with a whole lot when we get into next spring and start studying differential equations and the way that those the things that differential equations are modeling are describing what their behavior is going to be over long periods of time. So this idea of asymptotic behavior ends up being a very, very important one, and it's one that we're going to come back to several times over the next couple of semesters. So the next topic will be our last. It's going to be called anti-differentiation. All of the processes that we've been working with so far has been given a function. Let me apply these rules to find the derivative. Can we run that process in reverse? And ultimately, what does that mean? And what kinds of information can we get out of it? We'll talk about in the next lecture. Thank you.